So assignment related to photoelectric effect. The first 5 questions already I have recorded the session, so we'll discuss from question 6 and onwards. The photoelectric effect occur when electromagnetic radiation. The photoelectric effect occur when electromagnetic radiation of a suitable frequency is incident on the metal. Because when not all the frequencies can remove the metal electron out from its surface, there should be a specific frequency which is responsible for this removal of electron from the metal. When electron absorb, like specific frequency or a specific energy E is there, so minimum possible energy which electron required, that is called work function of I. So if the energy of the photon is equal to the work function or more than that, that electron will come out. The observation of a photoelectric effect provide an evidence which support the particle model of a light. So the photoelectric effect can only be like the particle nature of a light can explain the photoelectric effect. The wave nature cannot support this phenomenon. So we have a zinc plate is illuminated with a radiation, as you can see, a plate of a zinc which is illuminated with a radiation of varying frequency, like we're changing the frequency. The graph shows how the maximum kinetic energy of the emitted electron varies. So what is happening, like if we are increasing the frequency, this x-axis, we are increasing a frequency of a photon, it means we are increasing the energy of photon because E is equals to hf. So if the frequency increases, the energy of a photon will also increase. So when we increase the energy, first at certain energy or certain frequency, there is no photoelectric effect because that energy or the frequency is not sufficient to remove this electron out. Once the energy is equal, then electron will come out and further providing energy. It increases the kinetic energy. So on y-axis, we have the graph for kinetic energy of electron, but that is in electron volt. So increasing the energy, the frequency of a photon, it will also increase the kinetic energy. The frequency at which the line crosses the x-axis is known as the threshold frequency. What is meant by threshold frequency? So what is the meaning or a definition of a threshold frequency? That is the lowest or the minimum possible frequency for this photoelectric effect to occur. So threshold frequency is the minimum possible frequency at which this photoelectric effect can happen. Can occur. Explain how the existence of a threshold frequency supports the particle theory, not the wave theory. And asterisk question means like your answer should be, you should use a proper terminologies and it should be in a proper manner, like the things should be related to each other when you're explaining this. So first, according to particle theory, like in a particle theory, one photon can interact with one electron. That's the one thing. When light is having a particle nature, the first point is always where, like one photon, according to particle theory, one photon can interact with one electron, or one photon can absorb, one electron can absorb one photon at the time. That's the first thing. Then the energy of the photon increases as we increase the frequency. Like if E is equals to hf is there, so energy of a photon depends on the frequency of a light which is incident. High frequency means more energy is incident on the metal. So the energy of the photon depends on energy of the energy of a photon depends on the frequency so what will happen if the photon energy is less than the work function, as you can see from the previous graph on the previous page, that if the energy of photon less than work function, then there is no photoelectric effect, like no electron is able to come out. So there is no photoelectric effect in that case. But according to wave theory, like if light was having a wave nature, any frequency or light of any frequency should remove the electron from the metal surface. So that's the main difference. Like one photon can interact with one electron. Like this is a metal surface, and we have the electrons are there within the metal, a lattice of a positive ion and the delocalized electron, and a light of a certain frequency or a photon with a certain energy when it falls. If the energy of this photon is more than the work function, then it will come out, or more than or equal to, otherwise it won't come out. But according to wave nature, what should happen? Like if light is having a wave nature, then any energy, like example, because wave is continuously, like even though it's a 2 joules or 3 joules, but continuously it falls on the metal. So a time should come when this electron will have sufficient amount of energy to go out, but practically it does not happen. We observe specific frequencies, specific energy photons are able to remove the electron out from the metal surface, not all or any photon. So that's why it supports the particle nature rather than the wave nature of a light. Is it clear this part? How this threshold frequency supports the particle theory of a light, not the wave theory?
Yes, sir.
The next, radiation with a frequency of 2.4 exponent 15 hertz is incident on the zinc metal. Determine the maximum speed of emitted electron. So first, we know the energy is equals to work function plus the kinetic energy. So energy of the incident photon minus the work function will get the kinetic energy. And after getting the kinetic energy, we'll use the formula kinetic energy is half mv square, where m is the mass of electron, which is 9.11 exponent minus 31. And the kinetic energy we get from the difference, we'll get the speed. But how to get the energy of incident photon? So radiation with a frequency. So we have this frequency is given 2.4 exponent. So we can use this E is equals to HF. We multiply, like the frequency is there and H is there, so we multiply, we get E. But how to get phi? Phi is also equal to HF naught. F naught means like the threshold frequency. So for threshold frequency, a minimum possible frequency at which this photoelectric effect will happen or occur. So using this is a minimum possible frequency at which just is about to happen. So it is the threshold frequency, the F naught is equals to 1 into 10 power 15 hertz. So what we'll do, we'll work out the work function, which is HF naught. We multiply with the Planck's constant, we'll get the work function. And energy of the photon we already calculated, which is E equals HF. F is a frequency, H is a Planck's constant, so we get the energy. So energy of a photon is there, and the minimum possible energy work function is there. We subtract to get kinetic energy, and from kinetic energy, we'll use a formula half mv square to get the speed at which this electron is moving. I will calculate. This is one way, like we take a difference, or there is also another way because the graph is given and the frequency, as you can see, radiation with a frequency of 2.4 into 10 to the power 15 hertz. So what I can do, I can from this I can directly find the kinetic energy. When it is 2.4, so 2.1, 2.2, 3, and 4. So this is 2.4. So from 2.4, I will draw a line. When the frequency is 2.4, I will draw a line on the graph and I'll find how much is the kinetic energy directly. This is the second way because the graph is given for a kinetic energy. So that is 5 point, each box is representing 0.2 as there are 5 boxes. So 5.2, 5.4. So this is 5.4 electron volt. So the kinetic energy is 5.2 electron volt. But we need the kinetic energy should always be in joules because electron volt is, we cannot substitute the value in electron volt in the equation, any equation. We should use the SI unit, so which is joules. So this electron volt we have to convert into joules. So how to convert electron volt into joule? We have 1 electron volt is equals to 1.6 into 10 to the power minus 19 joules. So if we have 5.4 electron volt, so this will be X. So we cross multiply, we'll get the energy in joules, which is 8.8 into 10 to the power minus 19 joules. That's the kinetic energy of this electron, which is coming out. Now from kinetic energy, from its kinetic energy, we can work out the speed. The kinetic energy is half mv square. The kinetic energy is 8.8 into 10 to the power minus 19. Half the mass of electron is 9.11 into 10 to the power minus 31 kilogram. The constants will be given in exam. At the end of the exam sheet, you will find the constants. So you can use, you don't have to memorize this value, and then v square. Now we simplify this. This will be 2 into 8.8 10 power minus 19 divided by 9.11 into 10 power minus 31 and take a root, square root to get the value for speed. So when we substitute, this will give us the speed at which this electron is moving, which is about 1.4 into 10 power 6 meter per second. That's the speed at which this electron will come out from the metal surface. Is it clear, this part?
Yes,
the
sir.
calculation. Okay. In question 7, a student carries out an experiment to investigate the photoelectric effect by shining the light of different frequencies on to a particular metal. Describe how photoelectric effect take place. So you just have to write a definition of a photoelectric effect. What happens when light in the form of particle or a photon is absorbed by the electron? These electrons will come out the metal surface when the energy of a photon is more than the work function. So photon is absorbed by the electron, or photon transfer energy to the electron, and these electrons will come out from the metal surface. So light in the form of particle strike the metal when photon interact or is absorbed by electron. The electron will come out from the metal surface when energy of photon is more than the work function of metal. And different metals have different work function. So this is what happened, that if the energy is more than the work function, then only the electron will come out. Otherwise, it won't happen. The next question, the maximum kinetic energy of a photoelectron is determined for a range of frequencies, like different frequencies, and you can see the maximum kinetic energy. Graph is there. The list of a formula on this paper gives this expression that HF is equals to work function plus half mv square. Use this expression and the graph determine the value of the Planck's constant and the work function. Look, first, this graph is between what? This graph is between the kinetic energy and the frequency of the photon. So if this graph is there between the kinetic energy and frequency, where kinetic energy is on y-axis and the frequency is on x-axis. So I have to rearrange the equation because that's the maximum kinetic energy. So I have to rearrange the equation like y is equals to mx. So on y-axis, this is the kinetic energy. So I can say HF is equals to phi plus kinetic energy or Ke. So if I want to compare with the equation of a straight line in which y is equals to mx plus c, so on y-axis I should have a kinetic energy. So if I rearrange this equation, what I can, like phi will move other side, the work function will move other side. So I can say HF minus phi is equals to kinetic energy, or we can say kinetic energy is equals to HF minus phi. Now, when I compare with the equation of straight line, as we have equation of straight line, y is equals to mx plus c. So on y-axis, if I have kinetic energy, on x-axis, if I have frequency, what will be the gradient of the graph? The gradient of the graph will be equal to the h, which is a Planck's constant. And what about the negative y-intercept? So when it intersect the y-axis, the negative of the y-intercept, like this is the y-axis, so the negative of the y-intercept will be equal to the work function. So if you want to work out or find the work function, like if this was a graph between frequency and kinetic energy, so if we extend the point where it interact, like this point will be the work function, because negative y-intercept is this one. Positive y-intercept if it touch the positive side of y-axis. So on y-axis, if we have kinetic energy, x-axis we have the frequency, our gradient should be equals to Planck's constant, and the negative y-intercept will be the work function. So the question is, use this expression and the graph to determine the value of the Planck's constant. So what will the value of the Planck's constant? The gradient will be equal to value of the Planck's constant. And how to work out the work function of the metal used in this experiment? So we have this graph. So we'll extend, like using a ruler, you will draw a straight line, and the point, like using a ruler scale, you will draw a straight line, the point it will intersect the y-axis, that is a negative y-intercept, and that will give us the value of the Planck's constant. Sorry, that will give us the value of the work function, not the Planck's constant. Planck's constant should be the gradient. So I can work out the gradient of this line like using a y2 minus y1 over x2 minus x1. So first point on x-axis is x1. First point on y-axis is y1. Second point on y-axis is y2. So just we substitute the values, like this will be y2, this will be y1, x1 and x2, that, and we calculate the gradient, which is y2 minus y1 over x2 minus x1, that is equals to the Planck's constant. And after, what is about the work function? Because when we extend this line, the point where it intersect, like say minus 5.9, so minus 5.9 into 10 to the power minus 19 is the work function. Is it clear, this one? That how to work out the work function and the Planck's constant of this work function of the metal and the Planck's constant. And how you'll know that whether your answer is right or wrong, because Planck constant is a constant value which is 6.64 into 10 to the power minus 34. 6.6 into 10 to the power minus. So if your answer is within the order or the range, then it means you are doing right. But if your answer is not in this range, means you did some mistake. Like you should, the final answer should be in within this order. Like 6 exponent minus 34 is also correct. Even 5.8 exponent minus 34 is also right. But it should be in this range, like from 6 exponent, like 5.7 to 6.1. Explain why the results of this experiment cannot be explained using a wave theory. Like the same answers will be there, like why wave theory? Because on this graph, like there is no electron emission below a certain frequency. Otherwise, if there was a wave theory, if this was like light was acting like a wave, then any frequency should remove the electron out. Because what happened? The electron, when the light falls on the metal surface, so electrons are absorbing. Like if this is a metal surface and there are electrons within the metal, the delocalized electrons. So when the light is fall on the metal, any frequency, because like continuously the light is falling on the metal, so it absorb, and a time will come when this electron should go out, according to wave nature. But practically it does not happen. So explain why the results of experiment cannot be explained using a wave theory of this light, wave theory using the wave theory of light. So number one, like any frequency should remove the electron. But when we check the graph, not any frequency, specific frequencies removing the electron out from the metal surface. That's why the wave theory cannot explain the photoelectric effect. In question 8, a metal surface is illuminated with ultraviolet light with a single frequency. The electrons are emitted from the metal surface. It can be observed that the electron have a range of kinetic energy up to specific maximum. Explain how this observation provide an evidence to support a particle nature of a light rather than wave nature. So you can see a same question repeat many times, like why a photoelectric effect can only be explained by particle, not a wave. So first thing, what will be our points? The first point will mention that light travel in the form of particle, or we also call that as a photon, and one photon can interact with one electron. But if light was having a wave nature, then wave energy could build up. Like continuously the wave is falling on the metal, so energy should build up and any kinetic energy should be possible. Like there should be no limit. But because in a particle nature, one photon interact with one electron, and energy of a kinetic energy of electron depends on the energy of the photon. Or if the energy of the photon is equal to or more than the work function, then only this happen. Otherwise, it will not occur. So the points which we will mention, that according to wave nature, energy should build up, and any frequency or any energy can remove electron out from the metal surface. So any energy can remove the electron out from the metal surface. As a result, what will happen? As any energy can remove the electron out from the metal surface, so there should be no limit to the kinetic energy. So no limit for kinetic energy of electrons means any electrons can have any kinetic energy. But what happened according to particle nature? One photon interact with one electron, and energy of the photon depends on frequency of light, and when energy of the photon is more than the work function, the electron will come out. So these are the points which you should mention regarding the comparison between the wave and the particle. The next one is calculate the maximum kinetic energy in joules of emitted electron when the frequency of ultraviolet light is 2.5 gigahertz and work function is 2.3. First, what we have to do, we have to convert this work, because energy of a photon is equals to work function plus kinetic energy. That's a formula, the Einstein photoelectric equation. How to get the energy of a photon? Energy of a photon is hf. And work function is hf naught if the threshold frequency is given, and then kinetic energy. But because in the question we don't have the work function, we have the work function, we don't have the threshold frequency, but that work function is in electron volt. Whenever you use this equation, it should always be in joules. So you have to convert, like first getting the energy of a photon, which is hf. H is a Planck's constant, 6.63 into 10 to the power minus 34. That's a constant, multiplied by frequency, which is 2.5 into 10 to the power 15. So when you multiply, you will get the energy of this. When you multiply, you will get the energy of this photon, which is incident. That's 1.7 into 10 to the power minus 18 of joules. And the work function, that is 2.3 electron volts. So 1 electron volt is 1.6 into 10 to the power minus 19. So we have to convert. So 2.3 multiplied by 1.6 into 10 to the power minus 19. So we convert into joules. We multiply. This will give answer in joules. So 3.7 into 10 to the power minus 90 joules. Now we substitute the value, the kinetic energy. To calculate the kinetic energy, we just have to take difference, because E minus 5 will give us the kinetic energy, where E is the energy, that is 1.7 into 10 to the power minus 18 minus the phi, which is 3.7 into 10 to the power minus 19. When we subtract, we'll get the kinetic energy of this, which is 1.3 into 10 to the power minus 18 joules. That is the kinetic energy of this electron. Sometimes they ask for speed. Just we'll again use the formula. Speed, kinetic energy is half mv square. So we'll use that to get the speed of this particle. In question 9, the list of data formula in relation for this paper states that according to Einstein's photoelectric equation, hf is equals to 5 plus half mv square. Describe the photoelectric effect, include an explanation for each term such as hf, phi, and half mv square in the equation, and see the marks, 6 marks. So your answer should be in a proper manner. You should use the specific terms. So first thing, like, because we have to describe a photoelectric effect. So what happened in a photoelectric effect? Light in the form of particle or a photon incident on the metal. And this photon, one photon can interact with one electron. That's an important phrase, the sentence, that one photon can interact with one electron. Then the energy of the photon is given by a formula E equals hf. So hf is actually the energy of a photon, and it depends on the frequency. And where phi is a work function, minimum energy required to remove the electron from the metal surface. And if the energy of the photon is more than the work function, then the electron will come out. If there is less than the work function, then there is no photoelectric effect. So when we mention, like, the answer for this, the first thing, light travel or light strike the metal surface in the form of photon or particle. That's one thing. Then energy of the photon is given by the formula HF, which means it depends on frequency. The energy of the photon depends on the frequency of the light. Then one photon can interact with one electron. Then what about the phi? The work function of the phi is minimum possible energy needed or required to remove electrons. So how much energy, the minimum energy we need to remove electron, that's called a work function. If energy of the photon is more than or equal to the work function, electron is removed from the metal surface and the kinetic energy of electron is given by a formula that is half mv square. So these are the points you will mention related to the question. Then the last question, what is meant by the work function of a metal? How we define the work function of a metal? Work function is actually the minimum possible energy which we need to remove electron from the metal surface. Remember, don't forget to mention the surface, because if I want to remove the electron within the metal, I may need different energy. So work function, it's important that you completely mention like minimum possible energy to remove electron from the metal surface, because the energy needed to remove electron within the metal, that will be higher as compared to what is there on the surface. So work function is a minimum possible energy to remove electron from metal surface. That will, if you don't write, if you just mention minimum energy needed to remove electron, that's not the right answer. You should mention from surface. Then the last one, that is observation of the photoelectric effects support the particle theory. State one such observation and explain how it support particle theory of a light. Like how light can have a particle nature. So what happens if we increase the intensity of a light, it will increase the number of the photoelectrons, and one photon is released by one electron, or intensity increases the number of the intensity. When we, in terms of particle nature, intensity means that the number of photons increases. Or you can also mention, if we increase the intensity of a light, does not increase the energy or the speed of the electrons, and one photon release one electron, and the energy of the photon depends on the frequency, not the intensity. Like if we have a light is having a particle nature, so one observation which gives an evidence that or support that it is having a particle nature in photoelectric effect rather than a wave. So one evidence is one photon interact with one electron. That's one thing. Another thing, energy of a photon depends on the frequency, and there is always a work function, minimum possible energy, which we need to remove the electron out from the metal surface. If I increase the frequency, means I increase the energy. And what is the effect of this? The kinetic energy will also increase. So if increase the frequency, the energy will increase, and as the energy increase, the kinetic energy will also increase. But if we keep the energy same and we increase the intensity, so here what we are doing, we are increasing the frequency or the energy. But if we increase, so what we'll observe that electron will move faster, or the energy of the electron, the kinetic energy of electron will increase. That is what we observe. Second thing, if we increase the intensity, increasing intensity means that more photons are there, but energy is not changing. So if we don't change the energy, if like example, 5 photons are there, so 5 electrons will come out. But the kinetic energy of each electron will be same. So this is evidence that when we increase intensity, more photons are there, more electrons will come out with the same kinetic energy. But if we increase the frequency, we increase the energy of the photon. So electron will come out, one photon interact with one electron, and as a result, the kinetic energy of the electron will be higher. So any one of them you can mention, because this will also be observed, this also be observed. So either you mention increasing the points you can mention increasing intensity does not change the kinetic energy, it only change the number of electrons as one photon interact with the one electron, and energy depends on the frequency. Or you can mention, like, if we increase the frequency, energy of a photon increase, so kinetic energy of the electron will also increase as one photon interact with one electron. So any one of them you can mention. Is it clear, this part about the photoelectric effect?
Yes, sir.
Okay, so these are the questions from topic photoelectric effect.